Okay, so we still maybe have 4 minutes before we begin. Okay, so I received over the weekend some students saying that level 4 was not clearly presented, especially maybe for the part 2 of the task. So some students don't know how to handle that. I want to get a better understanding because I received multiple such emails. So just want to ask whether lab 2 is okay with more students, or can you give me some feedback? Anyone want to comment on lab 4? So what we covered, I think the TA covered, Nancy covered last Friday. Okay. Okay, I get some feedback on the chat. Okay, so I talked to the TA. So what we will do is that we will make the next lab again lab 4. So the deadline has been extended. Originally, it should be complete in 1 week. Now we allow 2 weeks. Okay, and so I will also be on in Friday's lab. Just make sure everything goes fine. Okay, at least for the first half of the lab. So the reason I think may not be clear is because part of the the data link layer Ethernet kind of content, like the ARP protocol and virtual LAN, we left to the TAs to present. I'm not sure whether they did a good job or not. So firstly, you need to understand the concepts, and then do the hands-on using the Cisco simulator. Okay, so I'm not sure whether that's a reason. So in this class, I'm gonna go through a few slides on that. Okay, just to make sure these concepts are clear. Okay, I believe that Jalal, the TA for the week earlier, should already explain what is ARP protocol and a virtual LAN, right? So, but just in case it's not clear, I will make a quick presentation before we go to Pgp protocol. Okay. Let me see the time. Yeah, I only see a few, 3 students giving feedbacks. If other students, can you give me some feedback on lab 4?
Yeah, I have the same sentiment. I really have no idea what's going on, and that's just me being honest, especially for part 2.
Okay, I see. So here,
I think a lot of us share that sentiment. Is just
Mhm.
none of us are that talkative. So that's all I gotta say.
Got it. Got it. Okay, I see more student feedbacks. Apparently, we need to redo the lab, and the TA will do a better job at task 2. Right, so part 2. I talked to the TA yesterday, and we discussed upon that. We will discuss, like the TA will do more illustration on part 2, right? And I will also go through some basic slides, just make sure those concepts are clear, at least. Okay.
I agree with you. I agree with you, Professor, because the time constraint is like, it's one factor. So they're trying to cover everything within that time frame. At the same time, it's really everyone will understand if they explain the concept first and then go through the lab.
Yes, I think July should have explained the ARP and the virtual LAN, right? Ideal. So how was the lab going? I mean,
it was okay. It was okay, but I know some people, they might need extra explanation if they didn't get the,
I understand. Yeah. So these concepts originally was supposed to be presented by the TA and then go through the hands-on stuff. Okay. So let me go through them today to make sure all of us are on the same page. Okay. Oh, but by the way, so so on Friday, if you have all those questions, just post it. I will be there. Okay. So let's really make sure things are on the right track, and you know how to do the lab. Okay. And then we have you basically have another week to complete that. Okay. I think yeah, I agree that the second part, I see the manual. It's not clear enough. Okay. The TA will give more give clearer explanations and instructions on how to do these things. Okay. And I will be there also. Okay. And just make sure everything is happening smoothly. And if you have any concerns, just let me know. I will see to it. Okay. All right. So because of this lab 4 issue that some students raised, so what I'm going to do is I will re-explain some of the concepts that should go before the lab. Okay. Including lab 3 and lab 4. Right. So here, I assume you can see the slides. Right. Everyone can see the slide. Yeah, who can give me some feedback? Okay, thank you. Yeah, so this slide has been shared on Canvas, the dynamic syllabus. Okay, you can download it. So basically, these are the relevant concepts about the local area networks, including the ARP protocol, Ethernet switch, and the VLAN. But because Ethernet switch, we have already covered that, I will go really quickly on those slides. Okay, I will mainly put more time on ARP and VLANs. Okay. So firstly is a concept of MAC address and ARP. Okay, so we know that IP address, right? So IP address is in the network layer, right? But we are now MAC addresses in the data link layer. Okay, so IP address are 32-bit, right? So and so this is basically network layer address. Okay, and so the MAC address is 48-bit. Okay, it's in the data link layer. Okay? It's one layer below the IP layer, network layer. Okay, and this kind of MAC address is hard burned into the network interface card NIC. Okay, and basically when the manufacturer produces network interface card, this hardware, right? So this ID will be hard coded. Okay, so you can never change it. And so whenever this network interface card go from this motherboard to the other, right? So then this MAC address will go with it. Okay, if you want to really switch, okay, the components into another computer. Right? So here's an example of how you can visualize a local area network. Right? So it's like the shared media as we explained. Right? So let's assume that in this local area network, we have 4 hosts. Okay, each host have a so-called adapter, which is the network interface card. Okay, and they have this 48-bit MAC address. Right? And so the thing here that is complicated is that when you are in the same local area network, when you route, actually just route using the data link layer, right? So because it's in the same piece of media, right? You don't need to go outside your gateway router, okay? But each machine may still have an IP address, right? So and usually when we send stuff, right? If you look at the TCP and UDP packet, we really send to IP address. We don't directly see the MAC address, right? But when actually you reach the local area network of the destination, you need to put the packet, right, and go down the protocol stack and unwrap, for example, the IP layer, then go to the Ethernet layer. Okay, and by that time, the routing can no longer rely on the IP address, right? It has to be relying on the MAC address. Okay, how to handle this, right? So let's take a look at. Okay, so the MAC address allocation is administered by IEEE. And so basically, if you are a manufacturer of the network interface card, you will buy a portion of this address, okay, and it will burn each address to a network card that you buy, okay. And then, so here we can look at MAC address like a social security number, right? So we talk about the bridge and how we get those addresses, okay. They do not have to be continuous and localized, okay. IP address is more like postal address, right? So you have to, so like phone number, you have to be localized, right? Each region you have the same prefix. Okay, MAC address can be any number you want, okay? But it's an identity. It's identifying your location. Okay, you can move around, right? But your social security number will never change, right? But your postal address may change, right? Like after a couple of years, you move to another address. Okay. And the MAC address is flat, right? So it's easily portable, right? You can move to another place. You are still taking this same SSN number, okay? And but IP address is not portable, right? So if you move to another location, right? So IP address prefix will be the prefix for that location, okay? So that's a corresponding concept. Now let's take a look at the ARP address resolution protocol, right? So the address resolution protocol called ARP. Okay. So as we said, when we route, let's say we don't go outside the local area network, right? LAN. So actually, when we communicate, finally it will go down to this network layer, this data link layer, right? Then we route through the Ethernet to the other machines. Okay. We actually use a MAC address to route. Okay. We're not using an IP address for the code. But actually, when you send stuff, you just know the machine's IP address, destination IP address, right? So in order to make sure when it's routing, it can get the destinations, maybe the MAC address, okay? We need to maintain a called ARP table, right? For each IP address, you need to have an entry saying, hey, what is the corresponding MAC address, okay? So there should be a mapping between IP address and the MAC address, okay? For the LAN. So the key is IP address, the value is the MAC address. And there's another field called the TTL, time to live. Right? So this is similar to what we described when we talked about the bridge. Right? Basically, because this IP address can be allocated to you, right? So you can hard code it by your local area network administrator. You can also use some dynamic protocol, DHCP, that can negotiate with the DHCP server and assign you a unused IP address, okay, to you, and keep track of what's happening. Right? So in that case, we need a so-called time to live, which means if you move, right, you leave this local area network, right? There should be a mechanism to remove your entry from the ARP table, okay? And the only way is, say, after 20 minutes, if there's no new message comes, right, I will remove this entry. Okay? But if you are in this local area network, right, so you keep communicating, right? So this will refresh, okay? This will refresh the timer. It will go back to 0. So unless you left, and then after 20 minutes, your entry will be deleted. Okay? Because this MAC address is really people can leave, come and leave. It's a social, it's a covenant with your laptop where you can just join and leave. Okay? Otherwise, if you keep all those entries there, like if you have a classroom and many students are having their classes, and then this table only grows and then will go out of control. Okay? So here's the ARP protocol. So we first think about the scenario that all the computers are in the same local area now, okay? And let's assume that, host A wants to send a datagram to host B, okay? A wants to send a IP datagram to host B, and but A's ARP table, right? The host A, it doesn't know. It knows B's IP address, but it doesn't know B's MAC address. Okay, so how can A find the B's MAC address, right? And then it can send in the data link layer properly in the same then. Okay, maybe the Ethernet. So for this purpose, A should broadcast the ARP query. Okay, the query packet. It contains B's IP address because A want to contact B. A only knows B's IP address, right? So it will put there. Okay. Remember, this is a broadcast message, right? If you have connected to Ethernet switch, then it will, because it's broadcast packet. Okay. The Ethernet switch will send to all the ports. Okay. What will happen is that every machine in your LAN will receive this upgrade. Okay. And what they will see is that the destination is FFFF. Basically, all the 48 bits are 1. Okay. This address is for broadcast, right? So basically, if your router see the address is all F, okay, it will broadcast it. Otherwise, it will send to your destination. Okay. Remember when we talked about the bridge. Okay. But FFF is a broadcast address. Okay. It will send to every port. And by that time, everyone will see this packet, right? The query. But because B is also connected in your shared media, right, in Ethernet, for example, okay, B will also receive this packet, okay, And B will check, hey, my IP address is really this IP address. Okay, and then B will, reply to A. Others will also receive it, but others say, hey, this IP address is not my IP address. They will drop it. Okay, so the frame will be sent to A, right? And using unicast. This time you know who is A, right? You just send it without broadcasting. B doesn't know, A doesn't know where B is, so A needs to be broadcast. Okay, and it will accompany, B's MAC address. And by that time A receives this B's MAC address, it will put into the output. Okay. So the student asking, what if the destination MAC address always FF? No, FFFFF is reserved for broadcast. Okay, you are not allowed to have a MAC address that is FFF. The network interface card manufacturer will not run such an address to your card because it's reserved. Okay? It's just meaning that if you see that, it's a broadcast. Okay. Right, so basically, whenever you send this, let's say this, let me. I think we have a diagram showing this later. So basically, your Ethernet switch, once the FFF will send to all ports. Okay. So let me see. For example, here you have the network interface card, right? And it's assumed it's connected by Ethernet switch. If you send anything, that address is something like this, it will just send to this one. Okay? But if your address destination is FFF, it will send to all 3 ports. Okay? I hope this answers your question. Alex, okay, thanks for confirming. Right, so yeah, so A will cache the IP to MAC address pair, right, to its ARP table. So each host, basically each network interface, each host will cache an ARP table, okay? But it will time out, as we mentioned, right? Because someone may leave this network, okay? And ARP is really a plug and play structure, okay? So you don't need any network administrator to be involved, okay? Because every machine, I don't know my destination MAC address. I just broadcast, okay? I just broadcast. And then that person also running the ARP protocol will know it needs to respond. Okay? Then after one broadcast, I will know that destination address. Okay, so that's the idea. So now let's take a look at the more complicated. Right? So if this is a local network, but it goes to another LAN. Okay, it goes to a router. So this is more complicated. Okay. So here, let's take a look at the scenario. So each host has an IP address and also a network interface card. And note that for your router, each interface, okay, each port has a corresponding, MAC address and IP address. Okay, so router, if you have 10 ports, then you have 10 IP addresses in the port. Okay, so yeah, so keep that in mind. Right, each port, each interface, basically, if you remember, this is called an interface, right? So each interface will have a MAC address, right? Okay, now let's focus on the addressing, right? So assume that B knows IP address, right? So A knows B's IP address. Of course, if you want to communicate with B, you know its IP address. For example, you use a DNS server, right? Get a domain name service, okay? Assume, all right? So we will discuss DNS later, okay? And you also assume that you know the IP address of the first hop router, the router that goes out, okay? So this can be obtained, for example, using the DHCP protocol when you join a LAN, right? So, or you can manually configure that, right? So you know the gateway router, right? So the gateway IP address, okay? You usually, if you configure your network, you know that there's like a IP address, subnet mask, and your gateway IP address, right? Often the last bit is 0, okay? And so these assume you know them, and also MAC address. So these will be configured, or by the DHCP protocol. Okay? Or the MAC address initially, maybe you will broadcast to, okay? And then this guy will reply using the ARP query. Right? The IP probably using so-called DHCP protocol. Okay, DHCP. We probably will find a time to cover that. Okay? Right. So. Now let's take a look at this situation. So what we want to do is that we want to send a packet, right? So from my machine, which was all ones, to another machine, which is all twos, right? So this all two machine is actually here to be, okay? So what we will do is that we will, because now we want to put into this shared media, right? So this is a LAN, okay? So we need to add another header, which is an Ethernet header, right? So I know that in order to send it out, I need to go to this interface, okay? This interface, right? Which is this address, okay? Which is here. Okay? These are sent to this point, right? And so the source MAC address is mine. Okay? I hope this is clear to you guys. And then this packet, because when you are in the data link layer to the routing, you don't see upper layers. You don't even see the IP address. But the green encapsulated packet, you don't see it. Okay, so you will route and then you will reach here. Okay, when you reach here, so the router will then use the IP address because it's in the IP table. Right? It will unencapsulate and get the content. Okay, and then find the hey, destination should go to this point. And we'll send your packet to this port. Okay, and now this port connects to another LAN. Right? So maybe this is the Ethernet switch again. So then we need to go back to go from IP layer to the Ethernet layer, data link layer. Okay, so what it will do is it will again, encapsulate in the Ethernet frame. Okay, so where the MAC address of the source will be, this port, like MAC address. Okay? And we know that we want to send the destination, right? So here it should already know. If not know, it will basically, using ARP query to know. Right? So the destination should be this. Okay. Now then we can route it. Okay. So when we route again in the Ethernet, we will not look at the encapsulated green part. Okay. We will only use the MAC address, and we will reach the destination. Okay. And then this will be delivered at the protocol stack. Right, and then you will receive. Okay, is this clear?
Yep.
Okay, thank you. Yeah, so then let's, I think the next two are very similar to what we just covered. Okay, so we will really quickly go through them. Okay, so this is Ethernet. Right, so Ethernet is switch. Right, so initially it's like a T connector, which is very slow, and shared media. Here, Ethernet switch you can send in fully duplex manner, which means you can these two machines can communicate. In the meanwhile, these two machines can communicate in full bandwidth without any conflicts. Right? And as the midterm has shown, right, so we have a preamble and we have the MAC address. Right, so for Ethernet, okay, and then we have some data payload and we have CRC. And Ethernet uses CRC for error code. And so these are the details explaining those things. We will quickly skip. Right. So Ethernet using CSMA CD. Right. So Markov talked about combined with CSMA, but using Ethernet switch probably we don't need this because now it's very clean. It's no longer like a shared media in some sense. It's I switch you to the right place. Okay, unless you probably send both stuff to the same port, then things will probably this will be running. Okay. And so there are a lot of Ethernet standard, right? So twisted pair and we go all the way to fiber. Right? So it's become faster and faster. And then we have the lens, and for the switch part, I think it's basically what we discussed earlier. So I will quickly, I don't want to waste time. Okay. So basically, if A sends a packet here, right? So because A is going to interface 1, so it will remember A's MAC address and the interface 1. Okay, and it will come down. Okay. And then here's another example. A is sent to A prime, right? This destination A prime. Then A prime will be flooded because so we don't know where A prime is. A prime can be here, can be here, can be here. Right? No one knows where A prime is. Okay, so it will be flooded, right? Because A don't know, which interface, and this bridge, this switch doesn't know A prime is on port 4. Okay, But when A prime applies on port 4, then we can enter this. Okay, and then next time if you send to A prime, you will only go to port 4. So this is basically covered. So I really want to skip quickly, and this can be stacked as we discussed. And so and there's an institutional go to external network. Right? So this is more like the AS we discussed earlier, right? Autonomous system. Okay. Right. So and there are some difference between switch and router. Switch are in the data link layer, and the router is in the network layer. Okay. So yeah. So now I will introduce in a little bit more details. Okay. So the VLAN. VLAN is virtual LAN. Right? LAN is local area network, like you have a switch. VLAN is saying, hey, I have a physical switch, but I don't want just a one local area network. Okay, I want a multiple, right? So, so in that case, we need a virtual technology, right? Even though you have the same switch, okay? It's like we have multiple switches connected by a router, okay? Then things look pretty nice, right? So just like what we see in the previous example, when we send from one LAN to the other, right? A router in the middle. But here in this example, we can think we have CS like a LAN, okay, and double E a LAN, and the computer engineer another LAN, okay, right. So now let's consider why we need a VLAN, right? So we consider a CS user want to move office to double E, right, but want to connect to the C switch, okay. This is possible. You move to like if you think about our university hall, right? So one side is CS, one side is mass, right? If the office, you want to occupy a mass side office, right? But you want a network to be inside the CS domain, okay? So how can you do that, right? So if you use a single broadcast domain, right? So the problem is that if you want to route through to another LAN, okay, so you must cross the entire LAN, right? So this is there's some security privacy concerns because you basically go through the LAN to LAN process we discussed earlier, and the router and these things, external things, see all these details, okay, and there are like privacy leaks. And this is a lot more costly because you need to go through maybe IP assignment like DHCP and the ARP table, all those things. But it's way more complicated. Okay? It's a lot of overhead. Okay? So in order to simplify this process, we have so-called virtual LAN, okay, local area network. Right? It switches, it supports, LAN capability, right? It can basically, it allows you to have multiple LANs, but it's virtual LAN. Right? It's actually in the single LAN architecture physically, but it can simulate multiple LANs. Okay, right? And most likely we will use a port-based LAN, which means, hey, each port belongs to. Let's say we can configure. We want to have two virtual LANs. Okay, local LAN. One is for CS, one is for double E, and each port can belong to only one of these. Right? So either CS or double E. Okay, but you can configure, for example, so it operates as multiple, virtual switches. Okay, so for example, if you send stuff in this LAN, it cannot reach this LAN. Okay, but so there's isolation. But what if, let's say here, I want to occupy a double E office for CS, right? So then you can configure this port. Okay? This port to be in CS LAN, okay? Because you have two LANs you configured initially, right? So if you use the software in the lab, you know that you can configure that. Okay, you first initialize a number of LANs, and you configure which LAN, which port is going to which LAN. Okay? So it can have so-called dynamic membership. Right? Ports can be dynamically assigned among LANs. But of course, you need to use different commands to achieve that in the software, okay? In the command console. And remember, for different LAN switches, their route is through a router in the middle, right? Like our two switch example. Okay, but these days, actually, your switch that supports VLAN actually have a embedded router. Okay, so you don't need an isolated router to connect these two virtually. Okay? They're actually combined, so-called combined switch plus router. Okay, so if you buy a switch that supports VLAN, so there's a router built in for this purpose. Okay, because you need the router to separate the two LANs. Okay, otherwise it's the same piece of LAN. Okay, and so the tricky thing is that, for example, now originally, let's say in EE we have 8 professors, but in computer science we have 7. Okay. Now the department grows, right? So EE has 3 more faculty members joining, and CS has 4 more faculty members joining. Right? But we only have 1 port left. Right? So how can we grow this VLAN? Right? How can we grow each local area? The only way is you have another switch with more ports. Okay? Let's say 2, 3, 5 up down to EE, and these 4 up down to computer science. Okay? But again, so here's the tricky part. So there are 2 different switches. Right? How do you say, hey, these 2 are actually belong to the same name? Okay? And these 3 belong to the same name, right? So there's doesn't seem to be a straightforward way to do that, right? You may think this is 1, 2, 3, 4. Right? How do you say, hey, 2 and 4 belong to the same name? Okay, right. So this is where the lab, the VTP, right, the protocol is doing. Okay? So T is trunk. So we have a trunk port. So basically 16 and 1 becomes the trunk. Okay? This carries frames between VLANs. Right? So defined over multiple physical switches. Okay? You can have multiple physical switches, but as long as they are connected by the trunk link, it's like operating like like the same piece of physical switch. It's kind of a trunk connecting. You think about it like a tree in that case. Okay, they are belong to the same tree. Right. These are made like the different branches or leaves. And so the frame forwarded within the VLAN between switches, right? So cannot be the vanilla Ethernet frame. Okay, because you think about it. So let's say this is a VLAN with ID 10, this is a VLAN with ID 20, right? So this is also 20, this is 10. Okay. Now if you send let's think about it, right? We want to send a packet from here to my VLAN here, right? You need to mention, hey, I'm go from VLAN 20 to 20. Otherwise, if you reach here, this switch don't know which VLAN should forward to, right? Maybe you will forward to 10, which is totally invalid because the local area network, you cannot cross the message. Okay, this is the purpose for protecting the local area network. Like in CS, we have the LAN.sys, .uab.edu. Okay, right, and the EE may have something like that similar, right? So in the school of engineering, so you cannot just hack into other people's departments local area network. Okay, and so here, this should be using a particular kind of new protocol. The frame format should be more than just the Ethernet frame. Okay, at least there should be a field carry the LAN ID, right? And one particular protocol is called H02.1Q protocol, right? That adds some additional hash field, okay, to support the frames that are transported over the this trunk port, okay, on this LAN. So that's what the VTP basically in the lab is doing. Right? So as here we told you that we need more ports, more fields, right? It becomes a new frame. That's why the protocol becomes a trunk protocol, right? So for Cisco VTP, there are proprietary protocol for these. If you are using Cisco switch, and so you need to have a particular, because there are different kind of trunk protocol, right? So you need to define the identifier, so you can pick an identifier which protocol you are using, maybe the like 802.1Q frame, so some particular protocol you are doing, right? And so the tag information here, you do have a 12-bit field, okay, just to remember what is the VLAN ID, right? So this also limits how large the ID can be, right? 2 to the power 12 for your VLAN ID. And there's also some priority bits you can set. Okay. And so because you add a new field, and when you have a regular frame, right, so stand through the trunk link, you need to change it to a 802.1Q frame, adding more fields. And because of this reason, the entire content of the Ethernet frame changes. Right? You need to recompute the error code. Okay, so this is recomputed status. Right, so that's basically the basics. I hope this will help in lab 4. Right, so I think Lab 4 basically asks you to add a bunch of LANs and add the trunk links between them, and then you can send stuff. Make sure I think the purpose of Lab 4 is something like this. Okay? Let me reopen this. Just make sure things are clear here. Let me see. Basically, Lab 4 asks you to create a VLAN structure like this, where you can define multiple LANs, VLANs. And then if it's cross router, so you have a trunk link, right, it want you to send a packet from here to here and make sure it can be received by people in the same domain, in the same VLAN. Okay, right. And if you send a packet from here and here, here to here is a trivial, right? So, okay, and if your simulated modules are configured correctly, and you should be able to send stuff here, and then this guy can receive stuff. Okay, that's the purpose. And of course, it will be more complicated, maybe multiple routers, okay, multiple switches. I see another question here. So there's a question about exam nodes. What do you mean by exam node? Can you clarify a little bit, Alex? You can unmute yourself and ask. Yeah, so maybe you can send me email. Okay, we can discuss this offline, right? Okay, so because I don't quite understand the question here. Okay, so let me continue with our Pgp project. Okay, so last time I think we finished the previous slide on the intra-domain, okay, intra-domain routing. So from this class on, we will talk about the inter-domain routing, okay? And so last time we talked about RIP and SPF, which are intra-domain routing in the same AS, right? And now, what if we want to route between different AS, right? Between different institutions, right? So, so we will need the Pgp protocol, okay? So here we are still at the network layer, and we want to set up routes between networks, okay? And each network is like so if you look at a LAN, right, it's really the basic thing, and different LANs can be connected by your interior routers, okay, and becomes your AS, okay? And then between different AS, we have another level, which is actually routed by Pgp protocol, okay? So the key challenge here is that how can we implement the provided policies, right? So if, let's say we have AT&T and competing with Verizon, right? So probably they don't want to route through their routers to help each other. Right? They want to compete for customers. But maybe some other service providers, they want to help. Right? And maybe another example is if we have the AS, which is actually UAB, right? We probably don't want to help route the traffic to Auburn, right? So because both maybe UAB and Auburn paying some service providers, and there's no duty for the institution to route the traffic to them unless that's the AS of the service provider. Okay? So how we can implement those policies, right? And create a stable process, right? We don't want to route and the latency change suddenly and take every packet taking different routes. Okay? So that's not desired. All right, so here are the AS concepts revisited. We can have multiple autonomous systems, right? So keep in mind, so we are talking about, is this router itself may connect to some, let me see. Yeah, I think I should put this. We connect to some VLANs, okay? But here we are ignoring those VLAN ports, right? We really just look at those connections between routers. So these are called interior routers that help routing the traffic between different LANs in the same network. Okay? And so if you how to define interior router, you can see all those ports of the router are just internal to the AS, right? And what do we call it? border gateway, that's a BGP, border gateway router. That's where if you have at least one link on a port, right? So that connects you outside your AS. Okay? Then it's a border gateway. Let me see. Right. So there's a concept called AS number. In shorthand notation, we call it ASN. So this is actually a identifier, right, for each AS, okay, autonomous system. And the AS number is actually a 16-bit value, okay, right? So, but particular values are reserved, okay, so you cannot take these values, just like FFFF for broadcast. Okay? But you can take any other values, but it should be unique. Right? So the different institutions, different AS, you should take a unique number. Okay, you cannot conflict with them, right? So right now there are well over, although there are a lot of numbers, maybe 1/3 of the numbers are used, over 20,000 AS numbers. Okay, for example, AT&T, they own a bunch of, those service providers say they have many, okay, because they are the autonomous system have routing, so maybe UAB only have one. Okay, AT&T has a bunch of numbers, AS numbers, and Spring has a bunch of AS numbers, and you can go to this link to download all the AS numbers in North America if you want. So regarding the inter-domain routing, so it's quite different from what happens in each individual AS, right? So maybe in my AS, let's say at UAB, I want to route using OSPF, right? Maybe Auburn say, hey, I want to use RIP. So they may have different configurations, policies, etc. Right? But now in the high level, right, between the AS, they must use the same protocol, which is the BGP, okay, border gateway protocol. There's only one protocol, okay, it's a BGP. So because they need to work together to ensure global connectivity. Right? If they are talking in different languages, and then some paths may not be connected. Okay? This is in contrast to the intra-domain routing. Right? So basically, within your AS, you have total control. Outside your AS, right? Different AS should speak the same language. So that's the analogy. So, so what are the requirements for the BGP protocol? Right? So as a unified protocol, it should be very scalable. Okay, there are so many AS, and it should have a scheme that the performance matters. Okay? It cannot be super complicated. Right? For your local intra-domain routing, you can have a lot of complications with it. But BGP, it should be simple, just like a router, right? Router standard forward concept. Okay? And that should be also ensuring like BGP protocol can guarantee flexibility in choosing routes, right? So for example, it should be cost sensitive, right? Even though this pass is fast, I don't want to route, okay? And maybe there's some policy, I don't want to route from my competitors' routers, okay? Right. And I don't want route for my competitor routers. Okay? And so another is, for example, you should be able to route failures. What if some router is down and the route no longer works, right? You should find a way that could gradually converge to a better route that can be reachable, right? So the question is, with these requirements, is BGP a linked state protocol or distant vector protocol that we see before? Right. So the answer is actually it's kind of a distant vector, but it's different. It's path vector. Basically, if you look at distant vector, we don't remember the paths. We just say, hey, A to B, what's the distance? A to C, what's the distance? Right? We only have a distance value. And most we record the next hop, okay, that we should go to. But here, BGP actually it records the entire path, okay, right? So when you route through AS, right, you already know, hey, AS1, AS2, AS3, AS4, then I reach the destination. So this is called a path vector, okay? So that's a little bit different. So here, let's go into the details about the BGP. Okay. So this protocol, the full name is called the Border Gateway Protocol. Right? It's pure in the border gateway. That's so nothing to your AS. And it's actually the de facto inter-domain protocol of the internet. Just like IP, right? IPv4, IPv6, everyone knows. So if you want to route through AS, okay, this is the only protocol, Pgp protocol, the only protocol. Okay? And it's also a policy-based routing protocol, which means, for example, if your path there's some AS that you don't like, for example, it costs too much, it's my competitor service provider's router, right? Or for example, I don't want to expose any information to that AS, right? Then you can route around this AS. You don't want to, even if the path is shortest, you might not want to do this. Okay, this is quite different if it's internal to your own AS, right? So you want the fastest, lowest latency. Okay. And again, so this is similar to the distance vector, right? It's the Bellman form. Okay, but it we call the entire path instead of just the distance value. Okay, so it's a relatively simple protocol, but it's actually not perfect. It's actually kind of complex, right? So you need a lot of manual configurations, actually. Okay. And another thing is that outside your AS, if you send anything out, then entire world will see the advertisement. Okay. And if you have any errors, everyone will see that. So this will screw up the global traffic. Okay? So you need to make sure the configuration is properly done. Another thing is that the policy driven by economics, right? So it really, so maybe I have a better route that can give you higher bandwidth and short latency, but that costs money. Okay? If you didn't pay me enough, like as a service provider, I will take the slower route. And it's really not just by performance. There's a lot of considerations. That's why we have so-called policies. And so regarding the BGP relationships, okay, so we have two kinds of AS. Right? So the first is, for example, providers. The providers need to route all the traffic passing through the provider's AS. Right? So because it's serving those customers, you are paying them to route the traffic through the internet. So the customer pays the provider. Okay, the provider routes the traffic. Okay, so let's assume that let's say, hey, how to say this? Let's say this is like three different providers. Right? This may be the Verizon. This may be AT&T, etc. Okay, right. And then different customers routed by different providers. Right. So maybe you want to talk to your friend who is using a different operator. So then how does this route? Right? So maybe there's a concept called peering. Okay, so the peering relationship. So hey, now I will route traffic to you, and you will route traffic to me. Right? So these AS will route each other without paying each other. Right? So you can pay, but after paying, maybe in order to route this traffic, right? Peer 1, this provider need to pay Peer 2 someone, okay, right? And pay Peer 3 in this case, right? But next time maybe Peer 2 also send a lot of traffic, right, to Peer 1. Then Peer 1's customer. Then Peer 2 need to pay Peer 1. Right? Here, this direction, Peer 1 need to pay. Then they decide, hey, that's too complicated. Let's just have a peering agreement. So they do not pay each other. Okay? So this is called a peering concept. Peer plus ING. Okay? So peers do not pay each other. Let's say Peer 1 and Peer 2, they are peers. Okay, Peer 2 and Peer 3 are peers. They can route each other. But unfortunately, if you want to directly send, for example, a message from Peer 1 right, to Peer 3, because there's no edge, no peering relationship between Peer 1 and Peer 3. So no, Peer 2, will not route your traffic to Peer 3. Okay, right? If you here we are saying you don't have a link peering between Peer 1 and Peer 3. Maybe it's unreachable. Okay, if it's in this topology, right? Because Peer 2 is just peering with Peer 1 for this, and then peering with Peer 3 for this. Okay, so there's no duty for Peer 2 to help you route packets from Peer 1 to Peer 3. Peer 2 gets nothing. Okay, the reason you have the peering relationship earlier is because you are mutually serving each other. Okay, so actually, ideally, this is pretty good if you can go through Peer 2 to Peer 3. But in reality, maybe they will go through a more costly intermediate service providers or something, that it will run. Right? Even though this is faster, there's no incentive to do so. Okay? So that's BGP. That's the complication that it brings again. Let's see what do we have. Yeah. So here, for example, they can have the provider can have a provider instance. Right? So the customers themselves can peer UAB and ARP. Right? So providers, there will be up-level provider help you do this. Okay. Right. So let's say here, this is UAB's AS. Right. UAB AS maybe you will not send, maybe send to ARP, but ARP and UAB maybe there's a lot of communication, but maybe this is ARP with some other universities like MIT and with, right? So, but because there's no peering between UAB and MIT, right? So they need to go through a service provider. Okay. So this is the concept here. Right. So there are tier 1 ISP peering and tier 2 ISP peering. So these are like AT&T and Verizon, they may peer each other. Okay? And so that you can route through the traffic right between different service providers. Okay, so this is called. What's the question? Yeah, I think Julian King. All right, so I think let me see. Yeah, so I think we should stop here because the time is up. Right, so I will be here for 1 minute and then we will continue on Wednesday. And if you have any questions, feel free to ask. We will not take attendance today because of the addition of the slides, which already took quite some time. Okay. But if you have any questions, feel free to ask me. Again, so my apology for the bad experience about the lab, and I will be on Friday's lab to make sure things are, smoothly. Okay.
Thanks, Doc. Have a good one.
You too. Thank you. Okay, thank you all. So I don't see any more questions. Then I will see you on Wednesday. Okay, thank you.
One question.
Oh, yeah, so there's no attendance.
All right, so tomorrow's the last day to withdraw, right?
Well, sorry, I didn't get what you said. Jack, can you repeat?
Yeah. So tomorrow's the last day to withdraw, right?
Last day to drop, you mean, the class, right?
Yeah.
Oh, let me check. So there's a UAB calendar, right? So let me see UAB. Let me make sure, okay? Last day. Yeah, so last day to drop is March 18th. I think it's passed, right? So let me see whether it's a right.
Oh, I mean, like withdraw with a W.
Withdraw, right? You mean?
Yeah.
Let me see. Withdraw is April 28th. Okay. Did this answer your question?
Oh, April 28th. All right.
Yeah. So yeah, just go to the UAB calendar. Okay, you will see. Okay,
I was looking at. I must have been looking at different years.
Okay. Yeah, this year is special, right? So,
yeah,
2021 is the kind of you need to follow this year. Okay, so it's very weird. Okay, there's no spring break and there's some awareness day, etc. So yeah, make sure you check that. Right?
Sure.
Okay. So any other questions? If not, I will upload the video and I will see you on Wednesday. Have a good day.